Before starting this video, let's have a quick test. Do you know this famous personality? Maybe you don't know him, so let's keep him aside. Do you know her? Or her? I bet you can't remember any of these faces because these people do not exist in this world. These are just the fake images generated by GANs, also called Generative Adversarial Networks. In order to understand GANs, we must first know whenever we talk about certain machine learning models, we know there is an input to the model predicts certain output from it. Now, if the input has certain labels attached to it, we can use those labels or the ground truth data with the predicted output to compare those values and calculate some errors using certain loss functions. Then these error values are back propagated to the model to update the weights in order to improve and train the model. Now this learning method is called supervised learning. On the other side of the coin, we have unsupervised learning method in which we don't have any labels attached to the input, and that is why we can't compare our predicted outputs to any ground truth data. In those cases, the model, instead of learning how to predict certain outputs, it learns how to discover certain patterns or distributions in the input data, and then use these distributions to provide some insights from the data. One of the popular unsupervised learning methods is Principal Component Analysis, aka PCA. If you want to learn more about this technique, you can just click on the link above and watch the video later on. Coming back to our unsupervised learning methods, there are other methods available in these techniques, and GANs is one of them. So let us dive deeper into this and see what is the anatomy of GANs. So GANs contains two major components. The first one is the generator model and the second one is the discriminator model. Now both of these models are nothing but a neural network model. The task of the generator is to take the input from a latent random variable or a random distribution and produce a sample output. In case of images, this could be a fake image. In parallel, we also have a real-world image dataset from which we take a sample output, and both of these samples are then passed to the discriminator one by one, where the task of the discriminator is to discriminate and identify those samples as fake or real based on certain predictions. These predictions are then passed to the loss functions in order to calculate some errors. These errors are then back propagated to update the weights of the generator and discriminator model simultaneously. This whole training process is popularly understood as a two-player game analogy. Let's look at it. And now it's the game time. So the game would be of two-player game where player 1 would be generator and on the other side we have player 2, which is the discriminator. Let's see how the game proceeds. The generator gets its first turn where with its current weights it tries to produce a sample fake image. The discriminator gets its next turn. The discriminator tries to update its weights such that it can predict the sample as fake or real up to its best capacity. After thinking about some time, discriminator easily predicts the sample as a fake image. 1 point to the discriminator. The next turn is of the generator. Now the generator tries to update its weights such that it could produce a better fake image for the discriminator. The discriminator gets worried. When the turn comes, discriminator tries to think much on the samples and tries to update its weights, which is not that easy now. Based on some thinking, the discriminator decides that the sample is a fake image, and again a point to the discriminator. Now this game goes on and discriminator gets points again and again until a point comes when the generator improves its weights so much that the sample fake image looks almost realistic to the discriminator. Now when the discriminator turn comes, discriminator being confident tries to predict the sample and assigns the image as real. This time generator got its first point, and that's the end of the game. The generator is the winner here and the discriminator is a loser. But before ending this game, I would like you to know that the main goal of our training is not that the generator should win, but it is that the generator should win over a strong discriminator model. Otherwise, there is no point of training the model. Let's get back to the place where we left off. Now we know how the training of GANs takes place as a two-player game. But let's see in the detail of how these loss functions can be used in order to calculate the errors and hence backpropagate it in order to update the weights of generator and discriminator in this two-player game. If we refer to the original paper of GANs, which was published by Ian Goodfellow et al. In the year 2014, they have published a loss function which is also called a value function, which looks like this. This looks complicated at first, but we'll go step by step and understand the significance of this term. But before proceeding, consider that the real image dataset which is provided to the discriminator is labeled as the target value of 1, and the fake image dataset which is provided from the generator is targeted as the label 0. First, let us look at the case where the real image dataset is provided to the discriminator model. Let us look at this table. Here, x is the value which is sampled from the distribution of real image dataset. Now consider two cases here. In the first case, the discriminator outputs a value of 0.1, and in the second case, the discriminator outputs the value of 0.9. As we know, the target value here is 1. Since we are considering only the real images, we want the output of discriminator to be as close to 1 as possible. Now out of these two cases, since 0.9 is closer to 1 as compared to 0.1, the second case is favorable in this condition. If we take the logarithm of these terms, we get minus 2.3 for the first case and minus 0.1 for the second case. And that signifies we have to maximize this logarithmic term in order to get output as accurate as possible. So that's the first objective function for discriminator. Now let us consider another case where fake images from the generator are provided to the discriminator. So the term g of z is the output of the generator, where the input z is the latent variable. Now consider two examples. In the first example, the discriminator outputs the value of 0.3, and in the second example it outputs the value of 0.8. Now since in this case we have the target value of 0 for the fake images, we want a value to be as close as 0 as possible. Out of these two examples, 0.3 is closer to 0 as compared to 0.8, so the first row is the favorable condition here. If I take the logarithmic of these values, we get minus 1.2 for the first case and minus 0.22 for the second case. So this signifies that I'll have to minimize this term in order to get accurate results while using the fake images in training. And that gives us the second objective function term for the discriminator model. Now since one is the maximization term and another is a minimization term, I can rewrite this second term in order to convert this term into a maximization problem. And as both the terms are the maximization terms, we can just combine them to rewrite the final objective function for the discriminator, which looks something like this. Now if you see, the term which is maximized is the value function that we saw earlier in the paper. Alright, so we know the objective function for the discriminator. Now for the generator, if you remember, whatever the discriminator wants to do, generator wants to do the opposite of that. That's why in that case, it wants to minimize this value function. And if you see, the first term that we have here does not depend on the output of the generator. So we can just ignore this term and rewrite our minimization problem as this. And because the objective functions here are opposite of each other, one being the maximization problem and other being the minimization problem, this is also called the adversarial network. Now we are ready to combine these terms into a final objective function for our model. So we can rewrite this term as the minimization of the maximization of the value function that we saw. That means whatever value function value we have is first maximized by the discriminator model by updating its weights, then that maximum value is minimized by the generator by updating the weights of generator model. This is also called the minimax function. Now we have some idea about the loss function that is used here. Let us see how this loss function is used in order to train the whole network. So first, the images from the real world image dataset and as an output of the current generator model are used to be fed to the discriminator model, which then predicts some values which is passed to the loss function that we just saw. After that, the generator model is logged and the error from the loss function is back propagated to the whole network where the discriminator weights are updated. Now since the generator weights are logged, they remain the same. After this, when the discriminator weights are updated, the discriminator weights are logged and this error is back propagated to the generator model to update the weights of the generator. Now this process continues until a point comes when the discriminator is not able to discriminate between the real and the fake image. Or in other words, we can say the discriminator outputs a value of 0.5 and hence could not label the image as 1 or 0, and that's the point where training stops. Let us look at this training process from another perspective. So here if you see, we have the black dots which represents the original data which is sampled from the original distribution which we are not aware of. Then we have the green curve which is the distribution modeled by the generator model. Then we have the purple line which is the discriminator model. Below you see X is the sample value which is sampled from the real world image dataset and Z is the latent space which is inputted to the generator model. Now if you observe here, the model distribution from the generator model and the original distribution do not match, and that means the real images and the fake images look pretty much different. Now in the first iteration, when the output of the discriminator model is passed on to the loss function and the errors calculated are back propagated to the model, in order to update the weights, we get a new model. And this model, if you see, is able to correctly predict the difference between the model distribution from the generator model and the original distribution, because the values which are to the left side of this point are predicted as 1 and the values after this line are predicted as 0. That's why we have a clear-cut differentiation. Now once we get a new discriminator model, the new prediction values are passed on to the loss function, which are then back propagated to the generator model now in order to update its weights. Now the generator model wants to minimize the value function which is maximized by the discriminator, changes its weights such that it is hard to differentiate between the real distribution and the fake data distribution. Now if you see, the discriminator model is not able to differentiate between them, and this process is continued until the generator model is improved to an extent such that the real images and fake images almost look exactly similar. In those cases, if you see, the discriminator model predicts a value of 0.5. That means it doesn't know how to differentiate between the fake and the real images. Now this is the point which is also called Nash equilibrium. So for the Nash equilibrium, there are two conditions that are met. In the first, the distribution from the generator model and the distribution of the real world image dataset becomes same. And the second condition to be met is that the discriminator output becomes equal to 0.5 for all the input that it gets. And that means we can't improve further from this point onwards. And that's the game over point. And then what? You can just use the trained generator model in order to produce fake images like these. Interesting, right? Now you can also try to generate your own fake images by using the link below to the website. And by the way, GANs is one of the most popular architectures in the field of generative AI. There is also another architecture which is gaining its popularity in the language models like ChatGPT. The architecture is called Transformers. Transformers gained its popularity after the paper "Attention is All You Need" is published in the year 2017. If you want to learn more about Transformers, you can just watch this video where I have explained the complete architecture and the functioning of Transformers in a step-by-step manner. Thank you for watching this video and see you on the other side.